Okay, so we've got a system of equations. We're going to solve this system by back substitution. Okay? Now, with back substitution, you can say that from the second equation, x1 is negative 1/2 x2. Okay? So now you can bring that back into, to do it by back substitution, this is all you can get out of this equation. Okay? So you bring that back here and substitute it in for x1, which gives you the equation 5 times negative 1/2 x2 plus 2x2 plus x3 equals 0. That's back substitution. Okay? And that gives you, well, that's negative 5/2, and that's 2, so you get negative 1/2 x2 plus x3 equals 0, so that x3 equals plus 1/2 x2. Okay? And then your solution is, and you wrote down the right solution, everybody wrote down the right solution. Okay? So x2 is going to be a free variable. Okay? So your solution is let x2 equal t, then as you got, x1 equals negative 1/2 t and x2, and wait a minute. Sorry, x3 equals 1/2 t, right? Makes sense now. How does that relate to the matrix you can reduce to solve the system, right? Well, if you reduce this matrix, you take 1/5 of the first row, you get 1, 2/5, 1/5, 0, and you get 2, 1, 0, 0, getting your leading coefficient here. Then you subtract 2 times the first row from the second, and you get 0 here. And then you subtract 2 times this from this, you get 1/5. And you subtract 2 times this from this, and you get negative 2/5 with 0. Okay? And that's the row reduction. And you get a solution that's equivalent. It's going to give you okay, in this case, you get x equals t times negative 1/2, 1, 1/2. I'm not sure you both did that, but you did something equivalent, but you can, from what you did, you can easily see this. Okay? I know I saw that at least once, maybe I saw it twice. Okay? Over here, you're going to get something that's equivalent. You might not get negative 1/2, 1, 1/2, depending on what you use for your free variable and so forth. There's going to be a multiple of this. Okay? So over here, what does this tell us? Well, this equation tells us that, well, you got x1 plus 2/5 x2 plus 1/5 x3 equals 0. And you have 1/5 x2 minus 2/5 x3 equals 0. Okay? From the second equation, you get x2 equals 2x3. Okay? Which is totally equivalent to what you got up here, that x3 is 1/2 x2. Okay? Just different versions. You got to get a different equation. That's no big deal. So the second equation implies this. So then the first equation we just plug in 2x3 for x2, we get this. And that gives you x1 plus x3 equals 0. That's 2 times 2/5 and 1/5 gives you 1. And x1 equals negative x3. If t equals x3, then x1 equals negative t, and x2 equals 2t. Totally straightforward. I was blocking it, you don't see it. That's exactly what you would write. So x equals, I'll write it out to give myself room, negative t, 2t, t equals t times negative 1, 2, 1. And negative 1, 2, 1 is just double negative 1/2, 1, 1/2, right? So if the t you use over there is double the t you use over here, you're getting all the same solutions. And you see, you're just going to get vectors parallel to this one. For any value of t, you get a vector parallel to this one, right? And this vector is parallel to this one. You just check the dot product is, oh yeah, you're not going to use dot product. But, you know, each component is double component you get over here. So you got to get exactly the same thing, okay? Make sense? And you could have used a different parameter over here, like maybe u, let u equal x3 and so forth, so you'd get u times negative 1, 2, 1, and you would see that this u is just half of what this t is. This t is double that u, okay? Now one thing you don't get, and one thing I saw, I think it was in your paper, Mark, is somehow you got down to a matrix with just one row. So I'm not sure what in the world you were doing with that, but you know, you got this solution. I don't know how you got down to a matrix with one row. But
well, my understanding is all of the rows, provided you do everything properly, they're all equivalent to each other, right? Based off of that, wouldn't they be interchangeable?
if two rows are multiples of each other, you're going to get a row of zeros, but you don't just throw that row out. Okay, so you're probably doing something, but the notation didn't match the notation any sane person would expect, which is expected at this point, because you got to be a little insane to do linear algebra. You got to be a little creative, okay? So nothing wrong with it. You know, your work was good, but if you're reducing matrices, first place get a 1 here and a 0 here, because that's how the reduction works. Not that you couldn't do something else. That's a standard way to do it, and it gives you a different form of the same thing that you do when you do back substitution. Okay? So,